Well, good morning. Well, I can't get the current slide to come up. Here we go. It is a little bit after 11, about 11:04 or so, something like that, on a Thursday morning, I believe it's the 10th of November 2016, and it's supposed to be linear algebra class, and right now I'm the only one in the room, so wish you were here. Where we left off, let me just go, oh, whoa, is someone coming in? There is someone coming in. All right.
At least.
All right. All right. I was going to go over announcements. I think you've heard most of them, about tutoring, about bookstore hours, and the math team not meeting this week. Maybe we'll get to next week. We'll see. And the others are that I have a faculty meeting at 2:30 today, so office hours are shortened from 12:15 to 2:15 rather than 3:15. And then also tomorrow's a holiday. Veterans Day.
And we're in linear algebra now.
Linear algebra now. Yeah, just finished being alone in differential equations.
So
Okay. All right. And
so jealous.
what's that?
I said I'm so jealous.
Oh, we're on page 184, section 4.5, basis and dimensions, and I think we're getting ready to start example 8. Okay.
That sounds good.
Yeah. Okay. And theorem 411, which by the way is, if a vector space V has one basis within vectors, then every base for V has n vectors. You can't increase or decrease the number of vectors. You can change them, but you can't change the number to form a basis. Okay. So it says, use that theorem to explain why each of the following statements is true. Here's the first statement. Let me get my pen activated. Oh yeah, I'm sorry, I forgot. Last class I didn't have anyone in here, so I never turned it on. And I can swap my lights around too. And this morning, in my first class, the projector went wacko. It was, let's see if it does it this time. Can't tell. Of course, there's nothing to tell on this one. This student back this way just had. It's been cold in here this morning. Yeah, it's showing up normal. It was elongating everything, and the bottom part of the screen there, I could write on it, but it would not show up here. And we tried a couple things. I wish I'd have just turned off the projector and turned it back on, but one of the students said he thought it had something to do with screencast-o-matic, so we fiddled with that and finally had to shut that down. And I went on to turn off the projector too, and I think that's all it would have taken, but we had to record twice, or 2 different recordings to finish the class. All right, here's A. Here's a set, S1. The set S1 is composed of these ordered triplets: 3, 2, 1, 7, -1, 4. Okay?
It says it's not a basis for our theory because we don't have 3 different sets.
Exactly. Because we know one basis for R3. That's what this is saying. This is not a basis for R3. Well, how do we know that? Well, one basis for R3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. We know that. That's the standard basis for it. Okay? Well, it has three vectors in it. So you can't have a basis for the same space, vector space R3, that has more or fewer than three vectors. So yeah, can't be. All right. Here's set R2, or S2. S2. It's the vector space x plus 2, comma, x squared, comma, x cubed minus 1, comma, 3x plus 1, comma, x squared minus 2x plus 3. Done. Okay?
Well, you have 2x squared, so that messes you up, doesn't it?
It says show the prove or explain why this is not a basis for P3. Not basis for P3. Okay?
Like I said, you have two x's, 2x squared, or no, 3x's, excuse me. No,
All right.
2x squared and x cubed minus
Actually, the easiest way to do this is to look at the count. Okay? You got 1, 2, 3, 4, 5
1. And you only need 3.
vectors in there. You only need, actually, I think 4. You need the constant x squared, and x cubed.
We don't even have constant.
Yeah. Huh? Second?
We don't even have constant.
Don't even have what? A constant. Yeah, absolutely. Okay. So that sort of wipes that out too. But you've got more vectors than you need, and it probably doesn't even span it in the first place. Okay. The standard basis is 1x, x squared, x cubed. Has 4 vectors. This one only has. This has 5. Too many vectors for a basis for P3. Another linear algebra applied. The RGB, that means red, green, blue, color model uses the theory that all visible colors are combinations of the 3 colors, red, green, and blue, known as the primary additive colors. Using the standard basis for R3, where red would be 1, 0, 0, green would be 0, 1, 0, and blue would be 0, 0, 1. Any visible color can be represented as a linear combination C1R plus C2G plus C3B of the primary additive colors. The coefficients Ci are values between 0 and a specified maximum A, which includes A, and C1, C2, C3, those are equal to each other. Color is grayscale. Strange word, I've not seen that before.
You've never seen grayscale?
No, what is that?
It's basically somewhere between white and black.
Right, okay.
It's just different colors of gray, because if you see in the picture,
Right,
when they're all together, it's white.
right,
And if you change each one the same or whatever, it'll just change it to gray and then to black. Just kind of change it.
okay. If you change,
Alright, so it's if they're all the same, right? It said when C1 equals C2, C3 equals C3, so basically the R, G, and B are all kind of like the same number. So if it's 3, 3, 3,
Right.
when you put them together.
sort of talking intensities.
Yeah, it
Okay.
it changes the color of each of them, but it comes together to make either a brighter white or a darker gray.
I see. Okay. I thought that might be what it meant, but this doesn't show me that, but I'll take word for it, because it seems like if you had say a brighter green and duller blues and reds, it would be greenish, not grayish, but I don't know.
Well,
Yeah.
see, that's what it's saying. All the C1, C2, and C3 have to be the same.
Right.
So they all have to be the same.
Oh, then that makes a grayscale.
Right.
Oh, so it's not when they're,
No.
okay,
They're all being used the same amount.
yeah.
Okay.
But these aren't, okay, never mind. Okay. All right. Okay, the color is grayscale with CI equals 0 representing black and CI equal A representing white, and then something in between would be, okay, got it. The RGB color model is commonly used in computer monitors such as in smartphones, televisions, other electronic equipment, but not just there. Recently, when I say recently, I'd say within the last 5 to 10 years, actually a Nobel Prize had something to do with this. You remember what that was? Probably is right in there.
LED?
Yes, because for, I can't remember which was first, it seemed like the red was the first LED developed, okay? And then shortly thereafter, if not almost the same time, came out of green. But no one quite could get a blue to work, okay? And finally, I think he was Japanese, though I think he may have been working with an American company, or there may have been 2 or more guys working on it, finally got the blue LED to work. And as soon as that happened, then we have LED light. Before that, there were Christmas lights, okay, red and green, but you couldn't have white light. As soon as they found the blue, then they could get LED white light. And that's why, now, the prize came many years after he did it, you know, a few years after he did it, or they did it. But it was, they had to find the blue before they could have a white LED light. So that's why fluorescents were around and incandescents for a while, a long time before they ever got a white LED, because they only had red and blue up to that point. Just another thing. All right, dimension of a vector space. And if and when you listen to the differential equation class, my eyes just started doing weird things. I could hardly focus. Now, this has happened a few times in the past, and usually it's followed by something similar to a migraine. I'm hoping I'm not going to get a migraine today, but it really, I don't see any sparkling light, which usually comes with the migraine. But this difficulty to focus was bugging me like crazy. But it's a little better now.
The numbers and stuff kind of...
Well, just reading what's there. It just sort of not focusing well. By theorem 4.11, if a vector space V, and I wonder if I've looked into that like too much because I was just doing it when I did that, and that may be causing part of that. If a vector space V has a basis consisting of n vectors, then every other basis for the vector space has to have n vectors. The number n is called the dimension of V. Boy, I've been wanting to say that word all the time we were talking about it, but they hadn't defined it till now. If a vector space V has a basis consisting of n vectors, then the number n is called the dimension of that vector space V, denoted by dim V. Okay, dimension of V equal n. When
V isn't very bright.
what's that? Yeah, absolutely. When V consists of the 0 vector alone, the dimension of V is defined as 0, not 1. 0. Okay. So, I'm trying to think, can you have, no, okay, yeah, that's right. When V consists of the 0 vector alone, the dimension is 0. My thought that ran through my head, can you have a vector space of dimension 1? And I was going to say, it's got to contain the 0 vector, else it's not a vector space, but it could also contain, say, anything on the real number line, or a polynomial degree 1, not just 0. Yeah, so that would be dimension 1. Okay, this definition allows you to observe the characteristics of the dimensions of a familiar vector space as listed below. In each case, the dimension is determined by simply counting the number of vectors in the standard basis. So dimension r to the nth would be n, because standard basis 1 0 0 0 0 1 0 0 0 0 1 0, yeah, however many of those it takes. Okay. Dimension of the polynomial, p sub n, sub n for polynomial, raised to the n for, vector spaces. Well, they're all vector spaces, but no standard kind of vector spaces. The standard with standard operations is, because p sub n is everything up to and including degree n, you have to include a degree 0, 2 to get the 0 vector in it, for instance. So then you'd have to have a 0, 1, 2. So if it's p sub n, if n was 3, you also have to have the constant, so that makes it 4. Okay.
You think it'd be
N plus 1.
Yeah, n plus 1. That's why we should have had 4 there.
Exactly, yeah. That's why 5 wouldn't work, period. There may have been other reasons the 4 wouldn't work, but you couldn't have 5. The dimension of a matrix, M by N matrix, with standard operations is, you have to have 1 for each entry, and since it's an M rows by N columns, M times N is how many entries you have. That then is the degree of a matrix M by N.
2 by 2 is 4.
2 by 2 is 4. 2 by 7 would be 14. 3 by 5 would be 15. Yeah. If W is a subspace of an n-dimensional vector space, then it can be shown that W is finite dimensional first, okay, and that the dimension of W is less than or equal to n. And that'll be exercise 75 will do that. The next 3 examples show a technique for determining the dimension of a subspace. Basically, you determine the dimension by finding a set of linearly independent vectors that spans the subspace. Okay? All right. This set is a basis for the subspace, and the dimension of the subspace is the number of vectors in that basis. That's what the dimension of the space is, number of vectors in the basis. Okay, so let's do example 9. I think I'll go to a clean page, just in case we need it. Determine the dimension of each subspace R of R3. So these are all subspaces of R3. Okay? A. W is such a subspace, and that consists of D, C, D, C minus D, C minus D.
Here, the screen cut out again.
Yeah, I just caught that. Comma C. Okay? Such that C and D real numbers. Okay, there's your set. Now, it's in 3 space, so it has 3 components. All right? C and D are real numbers. Okay. What is the dimension? I think it's asking. Yeah, determine the dimension of each subspace.
Okay, so it's got 3 parts.
Right.
So I would want to say it's 3, but
Yeah.
it only has 2 components, so I can't want to say.
Okay. Basically, what we need to determine is the number of linearly independent vectors that can make up that subspace. Okay? And I would contend to you that 1, 0, 0 and 0, 0, 1 would make up that whole space. Because then, because D times the first of those, okay?
Well, let's see, you said 1, 0, 0. Is that D equal to 1?
Yeah, D is equal to 1.
Then that would be 1,
Okay. Yeah, okay. 1, yeah, that would be 1, -1, 0, and 0, 1, 1. Okay? Those two vectors in R3 will form a basis for this one. Because any linear combination, I mean, make up a D, any old D. 3, okay? Give me a C, any old C. 2. So D is 3 and C is 2, okay? Now, the vector, that would then be 3 minus 1, 2, right? 3 minus 1, 2. Okay? Now, that can be made up of linear combination of this one, where 3 times this vector,
3, -3, 0.
yeah, plus 2 times this vector.
And that would give you, and you add them together, right? That would give you 3, -1, 2. Yeah.
Yeah. So that is a basis. Okay. So certainly does. Okay. A subspace could have been up to 3, but this is made up of a vector, a basis of just 2. Okay. Now, and did they choose the same 2? I don't think so. Doesn't
So
matter.
Are these vectors? Because those are.
Say that again.
These are vectors, right?
Yeah. Yeah, exactly. Now,
I'm
didn't
getting confused.
I didn't have to choose those 2. They chose actually one a little easier. They let D be 0 and C be 1, and then at 0, 1, 1. Well, that's how.
That's what I say.
And then, yeah, it did the same thing. Yeah, that would have produced the same one. 0, 1, 1, and they just did it in different order. 1 minus 1, 0. Yeah. Okay. And any vector you choose that fits that pattern can be then created from a linear combination of those 2. So that's the dimension is 2. Okay. B. W. They get the same name, is equal to the set of vectors, I'll put it this time, 2b, b, 0. 2b, b, 0. Okay? Where such that b is any real number. Okay?
It's at least one space because it can be 0.
Say that again.
I said, it's at least one space because it can be 0.
Yeah. Okay.
Next, if you let B equal 1, that would be 2, 1, 0.
Yeah.
But the 0 is always going to be just 0. You can't mess with it.
You can't mess with that. So basically, that basically gets you down to it can't be more than 2. The basis can't be more than 2 because there's no degree of freedom, so to speak, here. Okay, if this is 3 space, x, y, z, c is always 0. So you're on the plane. Now, are you strictly on the plane, or are you limited even on the plane? I mean, can any number on the plane work? I would say no.
It would have to always be an even x or whatever.
Yeah, x would have to be twice what y is.
Yeah.
And guess what that defines?
Yeah.
That would be squared.
Yeah.
Squared. No, that would be squared.
Yeah. Okay.
This is just twice that. In other words,
Line.
x equal to y. Yes, exactly. A line. And that line has to go through the origin, x equal to y.
So it is kind of one dimensional.
It is definitely one-dimensional. It's a one-dimensional space. So the dimension, to do it the way they do, d of this w, dimension of that w is 1.
This is going to be a fun section to do on the test.
Yes, of course. They all are, aren't they? Okay. The basis vector for that then would be 2, 1, 0. And any vector you choose, you can write it as some multiple of 2, 1, 0. B times 2, 1, 0. Whatever B you choose. All right. Let's do example 10. All right. Find the dimension of the subspace W of R4 spanned by, here's the spanning set of V1, V2, V3. And this spanning set happens also to be the set of these three vectors, negative 1, 2, 5, 0, three, 0, 1, negative 2, negative 5, 4, 9, 2. Those are your three vectors that span this vector space, subspace W in R4. It can't be more than 3. You're absolutely right. Let's see, what is this thing? Find the dimension. Yeah, the dimension can't be more than 3. It could be 3. Can it be more than 3? Okay?
So can it be 3?
Yeah. Does it have to be 3? Well, what we would have to do then to see if these are linearly independent. If they're linearly independent, then it is 3. If they're not, then it's something less than 3, which I would guess would have to be 2 here, but I can't absolutely swear it would have to be. So let's do it. It's spanned by this, but it's not necessarily a basis. It may be. To be a basis, it has to span it and be linearly independent. Two properties, okay? And what we have to do they actually show this? No, they don't, okay? So what we'd have to do, and there's a couple ways you could go about doing it, but to me, the best way to do it is to set up the matrix, and I think I mentioned this to you before, write these in columns. I don't know why the book hasn't addressed this yet.
Because, I mean, vectors are written in columns.
What's that?
Column vectors.
Yeah.
And these,
Yeah. But write it as a matrix, but
right.
Those things are in columns.
Columns.
And then let's see if we can row reduce. First thing I would do is change signs. Okay. Next thing.
Negative 2, row 1, plus row 2, and negative 5, row 1, plus row 3.
Okay. 1 minus 3, 5.
Negative 6.
Huh?
Negative 6.
I'm sorry.
Negative 6.
That last one? Yeah, negative 6, right. Okay. And that would be a 0.
Negative 15 plus 1, which is negative 14.
All right. So minus 5 times minus 3. And
25 minus 9, which is 16.
negative,
Yeah.
right? And
Copy that.
okay.
We can divide that second row by 6.
And we divide the third row by 16. And we divide the fourth row by 2. Or negative 2. And then those are all the same. So,
You can add them together. So it's singularities.
yeah. So it's easy to get any one of these rows. In fact, multiply this row by 8, that row by 3. Yeah. 3 times this one plus that gives you a 0. 8 times this one plus that gives you all zeros.
So you
Right.
have 2 rows of 0.
Yeah,
So
2 rows of
does
0.
that
So
mean
basically,
this would be only 2
dimension 2. Exactly. Dimension 2. Now, that I said was the easy way to do it. I mean, one way to do it.
I'm sure they have some kind of
Yeah.
convoluted.
No, well, no. I was starting to say this as well, but I thought this would be easier to show. But what I was also going to say, if you pick one of those, and I would just randomly, not randomly, somewhat for a reason, pick row the third vector and see if it was a linear combination of the other two. Okay?
5, 1 times what? 1 times 3? I mean,
Yeah. And that works too. But this was pretty easy to do, so why go through all that? I mean, it's the same kind of a procedure, but it's just another way to do it. And I mean, you could do that, and here's what it would be: that let's call it C1 times, let's just call it V1. Okay, that's what they called it. V1 plus C2 V2. Goodness, this is slow. Is that equal to, can you find that equal to V3? And
well, the first one, probably have to do something like C1 equal 5 and C2 equal 1/3.
or 0.
Oh, yeah, because you add them.
Right.
So
But that may or may not work. But yeah, here's how you do it a little more systematically than that, is actually doing that. That would be a minus C1, that's your first one, plus 2C2, wait,
No, minus
C1, yeah.
C3C.
Wait, yeah, got the wrong one going there, plus 3C2. I was looking at the wrong place. 3C2
Hold on here.
is equal to -5. Then 2C1 is equal to 4. Hey, right there we can figure out what C1 would have to be. Let's keep going though. 5C1 plus C2 equal to 9, and -2 C2 is equal to 2. Okay?
Okay,
So it looks like to me that C1 has to be equal to 2, and C2 has to be equal to -1. Okay? So I would go back and just plug and see if that works. Otherwise, that would be minus C2 minus 3 would be -5. Yeah, that works. And 10 minus 1 is 9. Yeah, that works. Now, the reason I go back and do those other two, it may be nothing will work, okay? And so you have to make sure that these two that you've chosen do, because if they don't work in the other two, then no, then there is no combination. Okay. So sure enough, we found out that 2 times V1 minus V2 is equal to V3. So if those, so the dimensions, that suggests to you that V1 and V2 are a basis, okay? Because V3 is a linear combination of those.
And if they're a linear combination, then that means it's only the space of the two making up the third.
Right.
The third doesn't define an extra part of it.
Exactly. It just lines up with the others. Okay. And they did the same thing. 2V1 minus V2 is equal to V3. Right? That means that W is spanned by then the set S1, not S, and S1 is just V1 and V2. Moreover, S1 is linearly independent because neither vector is a scalar multiple of the other. So you really need that step in there too. If this had been 7 space and you got it down to say 5, that one vector could be good, then you still have to make sure that these are linearly independent. So that's why doing this solves it right there for you. I mean, you eliminate anything extra, and you're down to it.
I kind of prefer matrices.
Yeah. So let's do 11. All right. Let W be a subspace of all symmetric matrices M22. What is the dimension of W? W is a subspace of all symmetric matrices in M22. And something kind of bugs me. Sometimes they put 2,2 and sometimes they write just 2,2. Well, I guess it's when they do letters, they MN. Well, why don't you say M, N? So I don't know. And then what is the dimension of W? Okay. Well, what does it mean to be a symmetric matrix? There's several things that means. But basically, and this is 2,2, so I think we can make it easier here. The first entry can be anything. Second entry could be anything. Has to be the same as that one, and this could be something else.
Basically, when you fold it over to the main diagonal, it's the same.
Yes, exactly. So what do you think the dimension of that is? 3, exactly. So the dimension of W would be 3. Because there's 3 independent things you've got there. A, B, and C are independent. B is the same wherever it is. So
if it was A, B, C, D, then it'd be 4.
Yeah, and if none of them had to be equal to another one. But you could say A, B, C, D, but then say, but B has to equal to C. If you wrote them that way, well, then those aren't independent. They are the same. They have to be the same. All right, so sure enough, that's what spans it. Okay. Not only that, they showed the spanning, and here's the spanning set of those. Certainly the first one, and it's almost exactly what we said, 1, 0, 0, 0. That's for A. For B, 0, 1, 1, 0. And for C, 0, 0, 0, 1. Any vector like this could be written as a linear combination of those 3. And it's the only way you can do it. Okay. I mean, that's the simplest way you can do it. Now, notice here, usually to conclude that a set S equal V1, V2 up to V sub n is a basis for a vector space V, you must show that S satisfies two conditions. S spans V and is linearly independent. Both things are required. If V is known to have a dimension of n, however, then the next theorem tells you that you do not need to check both conditions. Either condition will work. Okay? And the proof is left as an exercise. Isn't that nice? So, I guess I'll write this down for people without books. Okay? Let B be a vector space of dimension n. N, right? N, okay. 1. If S is equal to vectors V1, V2, V3, up to and including, is it Vn? Okay. Is a linearly independent set of vectors in V okay, then the conclusion of that is S is a basis for V. Remember, you can have more than one basis, but you have to have the same number for any of them. Okay. So, basically that says if it's a linearly, if you can show this set S has the n vectors it needs, and they're all linearly independent, therefore it has to be a basis for V. Secondly, if the S, same S, I'm not going to write it again, spans V, that vector space V, then that is enough to show that S is a basis of V, or for V. Okay. So you don't have to show them both. Okay, if you don't know the dimension of V, that it's n, then, and you have some set of vectors S, then they both have to be linearly independent, and they both have to span. It has to both be linearly independent and span. Okay, if you don't know what V's dimension is to begin with. But if you know what its dimension is, and the S has that many vectors in it, all you have to show is they're linearly independent, boom, it's a basis. Or, if you didn't know that, if you know S spans V, then it's also a thing, because if S spans V, and has n vectors in it. I'm sorry. I left that part out down here. But has n vectors in it and spans V, then it's got to be a basis. Because both of them have to be true, but if you know the dimension and the S has that many in it, then you, if you know either one of those facts, the S spans it or S, the set of vectors in S is linearly independent, then yeah, you got it. Okay, so let's do example 12. Testing for a basis of n-dimensional space. Show that the set of vectors is a basis for M 5, 1. Okay. Second?
Those are some tall matrices.
Yes, they are. That's a tall order, too. Okay. So, what we have...
That's a tall order.
Was that?
That's a tall order.
Yeah. here's a set of 5 vectors, but we're not calling it R5, okay, R raised to the 5. We're calling a, wondering if it's a basis for M51, okay.
Okay.
So, let's see, okay.
Well, I feel like it could be because they're,
Okay.
vectors.
Number one, what you notice about it, if you wrote them the way it's written now,
There's zeros.
and that makes it a lower triangular
Lower
matrix.
triangle.
Okay. Now, what's true about lower triangular matrices or upper triangular matrices? They are, as long as all of the diagonal entries are not 0, then I am wanting to say, I think it is true, yeah, that that is, if you combine those together in really any way, you're going to form a invertible matrix, okay? Because this system has only the trivial solution. And how do you know that? Well, when they wrote, I should be writing this down for others. I was trying not to, but now I remember. Not everybody has books. So here's your set of 5 column vectors, okay? The first of these is called B1, and B1 is made up of 1, 2, negative 1, 4, 3, 3, 4. Vector 2 is made up of 0, 1, 3, negative 2, 3. Okay. Vector 3 has components 0, 0, 2, negative 1, 5. Vector 4, or column matrix 4, however you want to call that, is 0, 0, 0, 2, negative 3. And vector 5, or column matrix 5, is 0, 0, 0, 0. Is it 2 or negative? Negative 2. Okay. Now, showing they're linearly independent would work because there's 5 vectors, okay? The matrix space M51 has 5 entries, okay? So its basis would be 5, okay?
So that's right.
Dimension would be 5, okay? But we don't know, we either have to show that this set spans that or that they're linearly independent. Linearly independence is the easier way to go here, because what you have to do that, you just show that C1 times this plus C2 times this plus C3 times this plus C4 times this plus C5 times this equal to the 0 vector. Okay, make sure I had enough zeros there. Can only happen if all of those C's are 0. Because if any of them is not 0, and you can get that, then you can write that one in terms of the linear combination of the others.
We know the first one's going to have to be.
Exactly, because 1 has to be 0. Okay? And if 1 is 0,
That's going to be
then
0.
this has 0, yeah. C1 is 0, then that's 0.
So
that has to be 0. And then if these two are both zeros, that means that this one has to be 0. 2 times C3 has to be 0. C3 has to be 0. So you just go down the line like that. Yep. Only solution that would work would be the trivial solution where all the C's are 0. Therefore, they're linearly independent. Therefore, this is the basis, a basis. Okay. So that's how you go about showing that. And that finishes 4.5. Homework exercises again. Goodness, I'm cold. Are any of the odds 1 through 5? Any of the odds 7 through 13? Any of the odds 15 through 19? Either 21 or 23 or both? Either 25 or 27 or both? Either 29 or 31 or both? Any of the odds 33 to 39? Either 41 or 43 or both? Do 45. Either 47 or 49 or both? Any of the odds 51 through 55? Any of the odds 57 through 61? Excuse me. Sorry. All right. Do 63, do 65, either 67 or 69 or both, and then the rest of those you can look at, think through, do as many or as much or as little as you like of those. Proofs and other things like that. All right.
I'm so hungry.
Me too. I have been hungry since the end of my first class. I don't know why.
I pretty much woke up and came here, so.
Yeah.
It's just,
Oh, wow. Not good. Okay. So let's,
Almost tempted to run down the vending machine.
yeah. Let's,
So
wait.
close.
Yeah. Let's clear this space. All right. Now moving on to 4.6. The rank of a matrix and systems of linear equations. Okay? 3 things we're going to do here. Find the basis for a row space, a basis for a column space, and a rank of a matrix. We'll find the null space of a matrix. So there's 2 new words here, rank and null space. And we'll find the solution of a consistent system in the form of xp plus xh, which we haven't identified what those are yet. So let's get going on it. This section we'll investigate the vector space spanned by row vectors or column vectors of this matrix. Then you'll see how such vector spaces relate to solutions of system linear equations. So let's start with some terminology. For an M by N matrix A, the n tuples corresponding to the rows of A are row vectors of A. You have M rows, but each row has n elements in it, so that's what makes them n tuples. So that would be a row vector. The n tuples corresponding would be a row vector of A, exactly. And they have the pretty little picture there. Similarly, in M by 1 matrices, the M by 1 matrices, where M is the number of rows, but you only have 1 column. I'm not doing these very symmetrically, are they? Corresponding to the columns of A are called column vectors of A. And you'll find it useful to preserve the column notation for column vectors. Okay, it's rather strange the way they wrote that. All right, let's do example 1. Hopefully this will be pretty easy. Here's a matrix A. 0, -2, the first column, 1, 3, the second column, and -1, 4, the third column. Okay.
You're writing like I do.
Well, I was doing the shortest or easiest to remember, so I wrote them that way. Okay. All right. What are the row vectors here?
0, 1, -1.
Okay. 0, 1. Oh, yuck.
It's just the rows.
I know, I tend to put commas when I don't catch myself not to put commas. Minus 1. And the negative 2, 3, 4. Those are your two row vectors.
It's funny because
Okay.
they wrote it with commas.
They did.
Yeah.
Okay, yeah, well, they're writing them as vectors then.
Right.
Okay. Or you could have written this as 0, 1, negative 1, and negative 2, 3, 4. But frankly, if I'm writing it as a row vector, then I'm writing that as a row of a column. It's called a row vector, but okay. And the column vectors, now look at that. The column vectors, they can't do that way. The column vectors are 0, negative 2, 1, 3, and negative 1, 4. And to be logically consistent, those would be the row vectors if you're calling these the column vectors. Why they wrote them otherwise, I don't know. Okay.
That's all we had to do.
That's what it said to do. In example 1, that for an m by n matrix, I know, pretty wimpy, isn't it? The row vectors are vectors in Rn. The column vectors are vectors in Rm, because you have that many tuples in them. Okay, 3 tuple for the row vectors, 2 tuples for the column vectors. Okay, this leads to the following definitions of row space. All right, row space and column space of a vector. My word, I think this week has just run me down. I don't know why particularly. Well, kind of, yeah. Combination of a big treatment on Friday of last week, election day on Tuesday, doctor's appointment on Tuesday, and then all the stuff about the election ever since Tuesday. So, okay. Let A be an m by n matrix. Okay. With that being the given, the row space, okay, of A is the subspace. Yuck. Goodness gracious. I don't know what that was becoming. It was just, it keeps getting worse, okay? It won't take it. There it is. All right, okay. I spelled is backwards and then started writing subspace. The row space of A is the subspace, okay, of Rn. Now, why Rn? Row space would have one row but n columns, because this has m rows in columns, so that's of Rn, spanned by the row vectors of A. Okay. The row space of A, definition here, is the subspace of Rn spanned by the row vectors of A. Does that mean that those vectors are a basis for that subspace? All it says is they span it. It doesn't say they're linearly independent. So no, it's just they span whatever portion of Rn that is, that's what they span. Okay, number 2, then the column space okay, the column space of A is the subspace of Rm. Now why m? because the column space, these are these, you have m rows, so it's a subset of Rm. That's how many are in there. Rm spanned by the column vectors. Same definition. Okay. And again, that doesn't mean it's a basis or anything. It just spans it. They'd have to be linearly independent for it to be a basis. Now, just in case it's going to get too crowded, let me go to a clean page here. And row equivalent matrices have the same row spaces. So, okay. Now, what that's saying is if you have a matrix, whatever size it is, and you start doing row equivalent operations, okay, then that next matrix that you do, whatever you do to it, it has the same row space as the previous one. And you keep coming down, and then finally at the end, if you have it in, it doesn't have to be Gauss-Jordan form, just Gauss form, that you have zeros below whatever diagonal you have. It may be step diagonal or whatever, and you have that. Then if you wind up with a row of zeros, the row equivalent matrices, they all have the same row space. So if you've eliminated some things before, they were eliminated before, whether you could tell it or not. Yeah, in other words, if you wind up with all zeros at the bottom. Okay. Let's see. Row equivalent. Where am I? Oh, that's the title of this theorem. Okay. So here's how they phrase it. If an M by N matrix A, okay, is row equivalent. Remember, we used to call that RE, row equivalent to an M by N matrix B, okay, then the row space of A is equal to the row space of B. Then row space of A equal row space of B. Okay. Back to your definition of row space. It's the subspace of Rn spanned by the row vectors of A. Okay? It doesn't have to be all of Rn, just that portion. So when you do your row reduction, if it makes it obvious not all the vectors are linearly independent, then you reduce that row space of RB. That also meant that the row space of A was also reduced. Okay. And I hope what I just said is sort of saying the same thing here. Because the rows of B are obtained from the rows of A by elementary row operations, scalar multiplication and addition, it follows that the row vectors of B can be written as linear combinations of the row vectors of A. The row vectors of B lie in the row space of A. Subspace spanned by the row vectors of B contained that the row. All right. Now, if a matrix B is in row echelon form, not necessarily reduced row echelon form, just row echelon form, that's Gaussian elimination, then its non-zero row vectors form a linearly independent set. Okay? Yeah, that's what your getting to row echelon form does, just like it's said above there. Okay? Consequently, they form a basis for the row space of B. Okay? And by theorem 413, they also form a basis for the row space of A, even though it wasn't obvious that was the case. The next theorem states that important result. I think we can do this one. If a matrix A is row equivalent is row equivalent to a matrix B, in row echelon form. RE is row equivalent and RE is row echelon form, just keep the difference, echelon form, that's the given. Then that implies the non-zero vectors of B and those, by the way, are row vectors. Yeah, non-zero row vectors. I thought they left off that. When you got it in row echelon form, that forms, different form, a basis, both for B and A. Obviously for B, but also A. Huh?
The form forms.
Yeah, the form. Okay. All right. Let's do example 2. I think we've got time for it.
4 minutes.
4 minutes, Find a basis for the row space A. The row space of A.
Oh, man.
Here's A. 1, 3, 1, 3. 0, 1, 1, 0. Negative 3, 0, 6, negative 1. Get it right? Yeah, 6, negative 1. 3, 4, negative 2, 1.
This is where you have to be real careful.
And yes, 2, 0, negative 4, negative 2. All right.
Okay, so when you produce this.
First, tell me what the maximum dimension of this is going to be. I would say 4. So you better wind up with at least one row of zeros. If you don't, you just created a new map. No, you made an error. So.
But most people don't like to want to start.
Right, including your instructor. Oh, I'm sorry. What you do first?
All right, so negative 3 row 1 plus row 3, and wait, that has to be positive.
Yeah.
Negative 3 row 1 plus row 4 though, and then negative.
All right. Got it? We're using row 1, 1, 3, 1, 3. I hope I copied it right. We're leaving alone row 2, 0, 1, 1, 0. And what's your new row 3?
0, 9, 9,
5. Hey, I've lost it. Where is it?
It'd be 3 times 3 plus 1, or 3 times 3 minus 1.
That's 3 times 3.
Oh, no.
Okay. 8. Okay. Hungry, I think. Okay.
Little on the low on the blood sugar side.
Yeah. Let me make sure.
That's
yeah,
right.
that's right. Okay.
I changed the math again.
Right. Forget I ever said that. Okay.
Huh?
Forget I ever said that. Okay.
Alright. So, negative 9 plus 4 is negative 5. Or, well, after this. Negative 3 minus 2 is negative 5. And then negative 9 plus 1 is negative 8. Bottom row, 0, negative 6, we can make 2 of them 0. That's
Okay.
or wait, no, you can't. Not really.
Okay.
Very similar.
Let's use row 2 and
Oh yeah.
yeah.
Make it work.
Yeah.
All right, so row 2. Where do we want to? Okay, just hit them all in one.
Well, see what happens.
Okay. -9.
1, 3, 1, 3, 0, 1, 1, 0, 0, 0, 0, 8.
Okay. If you add, wait, yeah, -8,
Yeah, that's negative 8.
and then the same thing below.
Yeah.
So if you add row 3 to row 4 and 5, you get 2 rows.
Basically, real easy to make that a 1, and that'll make these zeros. Is that okay?
I was just saying add row 3 to row 4.
Yeah, exactly.
Yeah, and then you divide by.
Then divide by that, yeah.
So it's 3 dimensional.
What's the question? What is the basis?
Basis.
The basis would be the rows of the non-zero rows of this one. So the basis for this would be 1, 3, 1, 3, 0, 1, 1, 0, and 0, 0, 0, 1. I think that's what it was asking. Find the basis for that, and that would be 1, 3, 1, 3, 1, 3, 1, 3, 0, 1, 1, 0, and 0, 0, 0, 1. They wrote them as vectors. I guess that's okay. Yeah, the dimension would be 3.
Okay, let's go get something to eat.
All right, we'll begin next time with example 3, top of page 191.
I hope the cafeteria has their
Card reader open. All right, I think here we can do 1 or 3 or both, and try doing any of the odds 5 through 9. Wait. We haven't defined rank yet, so you can do them or not. Yeah, hang off. We'll pick them up later. Okay. All right, that's done. Let's end the recording.